So I think the exam for this course is like, is it computer based or how is it?
Sir, computer based only.
Computer based only, right? So I don't think you will have negative marking, and I don't think so. But yeah, I need to check. Uh, Anything else
Sir,
you
in
wanted to
the
know?
question, sir,
Sorry.
in the exam, sir, all the question are like they will provide options, or like we have NAT type of question.
It will be something like similar to what you have in assignments. So like in assignments, you usually have the I mean the options and all, like the questions
MCQ.
which have like multiple choice type of questions. So some of them will be like multiple choice, some of them will likely be like numerical answer type, where you need to enter the answer in a numerical format, or some questions you may need to type, like if it's a conceptual question or something, like you may need to type, but I don't think it will be like very long answer type question.
Okay, sir. Thank you, sir.
Yeah, because it's like a computer based exam, so I don't think it will be like you have to type a lot of text and all. But yeah, so that I'll also be conducting another extra session on Tuesday next week, which is like 17th of September. So you can also attend that if you want. I am actually planning to conduct some like cover some examples related to how we can use MATLAB to solve some vibration problems. So I am planning to do that in the session. So and also if you have any other doubts or questions, like you can ask in that session. So it will be just before the exam. If you are interested, you can attend that session also. It will be
Sir,
Tuesday.
sir, when the hall ticket will be released?
Um, it will be released like some days before the exam. So I think, do you need to go to some center and like exam center and give the exam,
Yes,
or
sir. Yes, sir. Yes, sir. We have to go some specific center. Then we have to appear the exams.
so you have to travel to some like center? So will it be within your city, or sometimes is it outside the city also? Like,
Sir, I don't know, sir. This is the first time I'm doing course, so I'm not familiar with.
okay, I think they will give you enough time to plan your travel, or if needed. I think they will release it. I think well before the exam. So what is the exam date?
Sir, 21.
21. Okay. So most likely, maybe this Saturday, Sunday, I think they may release. But yeah, I don't know actually, because I am not the person who is involved in these like exam related things. I am just conducting these live sessions. So I am also not the right person to answer this question actually. So yeah, sorry, I can't uh, help
Okay,
much.
sir. Okay, sir. No problem.
Yeah. Anything else? Any other questions? Okay. So actually, one of the learners who usually joins, like he had contacted me and he told me that about this session conflict. So he said like he suggested that I should start the session by 7:15. So if you till then, like if like until the other people join, if they want to, if you have any questions, look, so just you can let me know those right now. I mean, related to the course content for this week, or uh, anything like that. So I'll be covering some. problems, like we'll be solving some problems in today's session also. So that so we already discussed, like 2 weeks back we discussed about 2 degree of freedom systems. So in that session, so I had described, like explained how to derive the equations of motion for a general like multi-degree of freedom system. So we covered it for a 2 degree of freedom system, but the same procedure actually we can extend it to multi-degree of freedom systems also. So we'll be actually following the same approach that we like uh, you know did like 2 weeks back, but slightly, because like in multi-degree of freedom systems it's like just slightly more complicated, so the equations will be more, the number of degrees of freedom will be more, so the number of equations of motions involved, those will be more. And then so you will be basically dealing with the system of lot of equations. And then so generally up to 3 degrees of freedom, so you can solve like 3 by 3 matrix equations at the most. Like once the degrees of freedom increases beyond 3, then the equations, like in matrix form, they become like very big. And then so if you want to solve like matrix equations for like matrices beyond 3 by 3 size, so then you like it will be really difficult to even like find the inverse for a matrix beyond like that size, like 3 by 3 and more. So in that case, so generally then we use computer based like methods to we solve equations, like by rather than solving equations by hand, we would prefer to use computers to solve those kind of equations. So we can also look at some example in MATLAB, like that if you want. uh, so that was the general agenda that I had in for today. Anything else you wanted to know, or any question that you had? So we'll just wait for 1 more minute if there are any other people who want to join. So and we'll get started in a like minute. Hello, good evening, Mr. Prashant. So I was actually waiting for like other people to join because of this multiple live sessions going on parallelly. But like I think now we can start with our session. Today I was actually planning to cover some problems related to multi-degree of freedom systems. And if it so happens that you have already covered that problem in the other live session, do let me know. I mean, so then I can will not cover that. So shall we get started? Okay, I think we can start by solving this problem. So here we have been given like a 3 degree of freedom system. So here there are like three masses and the 3 degrees of freedom are already shown over here like x1, x2 and x3. So we'll assume that in this system the masses are confined to move only in the x direction. So basically x1 and x2 and x3 and are the only 3 degrees of freedom. The masses will be allowed to move only in those directions. So to solve this problem, so we have to find the natural frequencies and mode shapes of the system. So here for this, the first step to solve this problem is drawing the free body diagram. And then the next step is to basically write down the equation of motion. So the step one is basically to draw the free body diagram. Then the second step is the equation of motion. And the third step is basically to solve the basically first like once we get the equations of motion, so we can write down them in matrix form and then solve the eigenvalue problem. Uh, so first setup and then uh, solve the eigenvalue problem. Right. So these are the mainly three steps and eigenvalues and then eigenvectors basically or mode shifts. So basically, uh, So those are the three, four main steps in this. So let us first start with the free body drawing by drawing the free body diagrams for each of these masses. So for the first mass M1, so let us assume that each of these springs is in tension. So for that, uh, let us assume that x3 is greater than x2 and x2 is also greater than x1. So that uh, we have basically that the spring is always in tension. So, or rather, we should write it as um x3 minus x2 should be greater than the free length of the spring, and x2 minus x1 is also greater than the free length of the spring. Let us call it as ls. So, so that will make sure that the spring is in. It's not necessary that we should assume that it is in tension or in compression, but like it just it makes our analysis more clearer and simplified in that sense. Yeah. So for the mass M1, there will be basically two forces. First will be due to the force due to the spring with stiffness K1. So which will be K1 X1. Now here again we'll make that assumption that x1, x2 and x3 are all measured with their respective equilibrium positions. So then we do not have to account for any static deflection as such. And then the force due to the spring K2 will be K2 into x2 minus x1. And then for the mass M2, for mass M3, there will be only one force which will be acting leftwards, and that will be K3. So those will be basically the free body diagrams for the system. So any doubt till now?
Sir, would you please let me know what is mean by LS?
So LS is basically just the free length of the spring. So here we are just making that assumption that this free length or unstretched length of the spring. So if the difference between the x coordinates of the two ends is such that that is greater than the unstretched length, that means that the spring is in tension.
Okay,
So
sir.
that, yeah, so that actually helps us when we specify that clearly, then we can, without any ambiguity, we can specify the directions of the force of the spring in any situation. So when we, I mean, specify that kind of an assumption, like that just generally makes our analysis more clear and easy to understand. So
Sir, can't we alternatively say x3 minus x2 is greater than 0? Will it suffice, sir?
x3 minus x2 is greater than 0 will be the case if like so if I mean, yeah, if they x3 minus x2 is greater than 0 will also suffice, but like if x3 and x2 are, let us say, absolute coordinates, I mean, like they, like if it is like measured with respect to, let us say, some this kind of an axis, like
Okay, sir. Okay. Yes, sir.
then we might, or otherwise if they are measured with respect to, let us say, if this was their equilibrium positions for each of them, and if x3, x2, x1 are measured with respect to those respective equilibrium positions, so then in that case we can say that this is greater than 0, so then that will be sufficient, because then the origin for each one is different in that case.
Yes, sir.
Yeah, but like let us say if it's like a more general case, that like let us say this is our origin, and like so then in that case we can specify with respect to ls that. Okay, so then let us proceed to write the equations of motion. So for the mass m1, let us write down the equations of motion. So so this will be the equation of motion for the mass m2, and then for finally for mass m3 is minus k3 x3 minus x2. So we can now write down these equations in matrix form now. So it will be like, what will be the coefficient of x1? Sorry. Uh, so like once you are used to, I mean, writing matrix equations, so you can like skip steps and just directly write it by inspection. So I'm skipping the step of rearranging the equations of motion, like rearranging the terms on the left hand side and then equating them to zero. So this, like basically this is the matrix equation, and like yeah, for the third row, so we have minus k3 and k3. Yeah. So this will be our basic matrix equation. So this will be our mass matrix. This will be our vector x double dot vector, and this is our stiffness matrix, and this is our x vector. So we got the equation in that general form of m x double dot plus k is equal to 0 vector. Now to get the natural frequencies, what do we have to do now? What is the next step to get the natural frequency? How do we get the natural frequency now from using the equations of motion? So basically we can make a substitution here, that x is, so x vector is some v vector e to the power some j lambda t. So where lambda is an eigenvalue, or basically one of the natural frequencies. So v vector is the set of x1, x2, x3 like amplitudes, and e to the power j omega t is the solution. So this, let us say this is our trial solution, and let us substitute that in the equation of motion. So what we get is that, so we have substituted x so x dot is and x double dot is minus lambda squared into x vector. So we make use of this fact in that this, and what we get is an equation of this form. So mx double dot plus kx equal to 0 becomes, so it becomes an equation of this form. Sorry. So now, so here now lambda square becomes an eigenvalue. So this is like the classic eigenvalue problem type setup. So if you compare it with the usual eigenvalue problem type definition, so now we can determine the natural frequency by solving the eigenvalue problem here by using that determinant of this matrix k minus lambda square m is 0. Now let us write down what are the elements of this matrix K, determinant of K minus lambda square M. So let us refer to our previous equations of motion. So K1 plus K2 minus lambda 1 lambda square M1. So in multi-degree of freedom systems, basically you will have a lot of equations of motion. So you will have to do a lot of algebra. So we need to patiently write down all the equations in matrix form and then solve the expand the determinant and then write down the characteristic equation, then solve it. So all these steps we need to do patiently. So because the in multi-degree of freedom problems, like even if you just increase the degrees of freedom beyond 2 or 3, the problem becomes quickly like very complicated to solve, like in terms of algebra basically. Conceptually all of them are like very similar, but yeah, so that's the thing. So even to arrive at any conclusion we need to go through a lot of algebra. So that's the issue in these kind of problems. Excuse me. Excuse me. So this is the determinant that we need to solve for. So we need to expand this determinant. But now before we expand that, we can use now the information that is given to us. That is So the K1, K2, K3 are related by some way. So K1 is K, is K2 is 2K, K3 is 3K, and also likewise. So let us make use of this information. So K1 plus K2 will be K plus 2K, which is 3K, and M1 is M. So it will be, so the first term will be, so K2 plus K3 will be 2K plus 3K, which is 5K, 5K minus, sorry, so just check whether I have written all the terms in the matrix correctly. So uh, just please check and let me know whether I have written all the terms correctly. So in this case, like one needs to be careful. So because even if one term just goes wrong, then the entire thing will just go wrong. So now if we expand this determinant, so these are the terms that we get for the determinant. So it becomes 5 into 3, 15, 15 minus 9, which is 6 k square. So just hold on for a moment. So 6 and 15, 15 and 21 mk lambda square. So basically this is a cubic equation, and so for that we what we can do is we can divide the um, divide and multiply by m cube, or let if you want to slightly simplify this, or we can just like expand it as it is. So basically what we will get is like a cubic equation in lambda, uh, not exactly cubic, it will be actually uh, so I have made a mistake here, so it should be lambda to the power 4. Yeah, so it will be an equation in terms of lambda to the power 6. So it will be a 6th degree equation, or you can say if we put some lambda square is some omega as a substitution, then that will be a cubic in that omega. So we can find out the roots of this equation and then get the natural frequencies. So do you want me to solve this further, or do you want to like try it on your own, and then shall we proceed to our next problem, or okay, okay, fine. Yeah, so it's like it will be like a very big equation, and then what to get the mode shapes, what you can do is basically uh, you can, so let us say if, so by solving this equation, so you will get the three eigenvalues, let us say lambda 1 square, lambda 2 square, and lambda 3 square. See, if you get a cubic equation, so either you can use your calculator. Um are you allowed to use your own calculator in exam? You aren't
Sir,
done, right?
they will provide on-screen calculators.
On screen. Oh, then it may not have that cubic equation type solver. I don't know. I mean, it may not be that much.
No, sir.
So in that case, I think if at all you get a if at all you get a big cubic equation type thing, so they will make sure that the cubic equation is simple enough that you can just find the roots by inspection, like that this will be definitely one of the roots, so you can solve it. Like it will be, they will make sure that it will be solvable, like without any much, that I think they will make sure, because generally time will be less, and so then you cannot just keep on solving one question for half an hour and just solving one cubic equation like that. So they will, I think, make sure that it is simple enough to solve it easily. Yeah, so in this case what I was going to say is that, so let us say if you solve this equation, let us say, which is cubic in lambda square, so or rather it is lambda to the power 6 equation, but if we substitute lambda square as some variable, then it is cubic in that variable. So lambda 1 square, lambda 2 square, lambda 3 square. So let us say these are the three eigenvalues and three natural frequencies, like correspondingly three natural frequencies. So now what is the eigenvector v1, v2, v3, or mode shapes? In other words, like mode shapes. So what are these mode shapes or eigenvectors? So they are basically relative amplitudes of each of the masses, or so relative proportions of these amplitudes of each degrees of freedom. So in this case, x1, x2, x3 actually mean the displacement of these masses. So they are basically the relative proportions of the, when the system is oscillating at its natural frequency, what are the relative amplitudes or proportions in which the amplitudes are for each of the mass when the system is oscillating at its corresponding natural frequency. So now how do we find out these vectors v1, v2, v3? So then for that we will have to solve again three simultaneous, like, systems of equations. So we had got the earlier equations of like motion. We have to basically solve this equation for each eigenvalue, or so if let us say this is j, so where j is can be 1, 2, 3. So if we solve this simultaneous system of equations for each, uh, so then, because this matrix is already singular, so then you will get basically I mean the same. So if you solve this system of equations, so there will be like infinitely many solutions to this, because this matrix is singular, because uh, this is like, for this to have non-trivial solution, this matrix has to be singular, so, and which will be like infinitely many solutions. So there will be basically, like, you will get an eigenvector, so let us say x1, 2x1, and let us say 3x1 or something like that. So so it will be basically the, so we can simplify the eigenvector to be 1, 2, 3 or something like that. So for each eigenvalue, we can get the corresponding relation between each of the x1, x2, x3. So that is how we can get the mode shapes. So do you get how we can get the mode shapes in this case? Any doubts on this? So you will basically use this equation itself, like this matrix itself. So and then solve like for the eigenvector for each one. So it will be basically, so this is like x1, x2, capital X1, capital X2, capital X3. So they are basically the terms or columns of the or basically the column or vector, like let us say Vj for the, like corresponding to the jth eigenvalue. So this is the jth eigenvector. So this is the vector equation, and what we get from this is like if we solve for these equations simultaneously, we will get, so we will not be able to get a unique solution for this. So we will get a like infinitely many possible solutions, but we can reduce it into some like let us say we can express x2 in terms of some x1 and x3 also in terms of x1, and then find out what is the relative magnitudes of x1, x2 and x3, and then we can find out a reduced form of that eigenvector uh, in terms of the jth eigenvalue. So here lambda j is the jth eigenvalue. So so if we let us say consider the first row of this equation, so So this will be one equation, and let us say we consider for simplicity, let us consider the third row of this equation. So we now we can express x1 in terms of x2 and x3 also in terms of x2. So x1 will be k by 3k minus lambda j square m x2, and x3 will be so basically we can write down that Pj is this term 2k by 3k minus lambda j square m, then 1, and then 3k by, so like that we can write down as the, this is like all these terms are in terms of x2, so but x2 can be any real number, so the simplest form of the eigenvector can be like this way. So is it clear like how we get the eigenvector or mode shape? Okay. Okay. So yeah, so then I think we can proceed to the next problem. Yeah. So in this problem we are it is shown that like there is an aeroplane. So we can consider a simplified model for this aeroplane. So we have to find out basically the first we have to derive the equations of motion for this, and then derive the natural frequencies and mode shapes. So we this approach will be similar, but what thing that we have to do here is, so we have to now to get the natural frequencies of this aeroplane in a simplified manner. We can consider a simplified 3 degree of freedom model here, that we can lump basically things together. So we can consider the body or basically the fuselage of the airplane as one single mass. Then the mass of the wings and the engine together as another mass. And then because of the symmetry, there we can consider it as like two different masses at the ends. And then we can model the wing which is basically fixed to the fuselage, so that as a cantilever beam, and consider the basically the stiffness of the cantilever beam for a, let us say, for a point load applied at the end one end of the cantilever. So we know what is the stiffness, or basically the deflection ratio of the deflection, and the force, like the force per unit deflection in, or basically the stiffness of the cantilever beam. So we can model it in that way, and then we can basically get a simple spring mass system model of this very complicated system in this manner. So this is shown in the all the three diagrams over here. So first we have the front view of the aeroplane, and then how we progressively extract a simplified model out of that. So now our task is to first derive the equations of motion for the airplane using this 3 degree of freedom model, and then use these equations of motion to find the natural frequencies and mode shapes of the aeroplane. So let us start with the equations of motion. So is the question clear? How we basically come to this model? Is that clear to you? Yeah. Okay. So then now what remains to be done is to basically write down the basically draw the free body diagram for this system, and then derive the equations of motion, and then solve those equations of motion, like basically set up the eigenvalue problem, and then get the natural frequencies, like in the similar way that we discussed. I mean, any practical problem, uh, getting to this step itself is the most toughest job actually. What is the challenge is always to uh, first get to know like what is the simplest and most practical model that is enough, like which has enough accuracy for our analysis purpose. So that's the challenge in any practical problem. So this decision of what model we should use, it generally depends on like what is the level of accuracy we need, what is our like basically the purpose. So here our purpose is to just estimate what is the natural frequency and mode shapes in a very broad sense. So this will give us some idea of the natural frequency. So the actual natural frequency may be somewhat different, and this because this analysis is very much simplified. Now let us say if this is like if when we generally also model for a car, we have different levels of modeling detail depending on what is the purpose, and also it depends on how much data we have with us, like how much information we have to so we can create a model with like several hundreds and thousands of parameters, but at the end of the day we should also have the values of those parameters so that we can you know use those parameters and get some useful results. So it's a interesting thing, and it is challenging to first get to that level of what is the model that we should use, and then the next steps are like will subsequently follow. So we do some simplifying assumptions. So here our simplifying assumption is that the aeroplane, different parts of the aeroplane can be modeled as a lumped system. So we can consider them as like point masses, like the mass is concentrated at a point, although the system is actually a distributed mass system, but we are simplifying it to be a lumped mass. So so I have picked up this problem basically to illustrate that so in textbook you can textbook or examinations you will find directly things like this. This is the system. Now write down the equation of motion and then solve and whatever. But getting from this level to this level is like, let us say, if the total amount of work is some x, so I would say this is like 80% of the work is this itself. Like most of the challenge lies in here itself, and then the further challenge is like just solving the problem, or say like solving the differential equation and that. So I hope this motivates you. I mean, or it helps you understand in a broader context what is the significance of what we are actually studying. So does that help? Yeah. So just hold on for a moment. So there is a lot of background noise nearby. So I'll just let me just make that. So I hope the background noise has reduced slightly, but um, because of this Ganesh Chaturthi festivals, like all these processions are going on, so we can't help. Like, I mean, we have to bear with the noise. I hope it is not disturbing to that extent that you cannot hear what I'm saying, right? It's not, you can hear me, right, properly. Yeah, so let us come back to our problem of this getting the natural frequencies of the aeroplane. So physically, what these natural frequencies would be is like because of the elasticity of the wings. So the wings are made up of some flexible material, and because of the um, the non-uniform pressure distribution along the wing. So wing thickness also changes as it goes from the fuselage, like the location of the fuselage up to the tip. The thickness of the wing will change, and then its width will also change. So the wing will also be tapered. So it won't be like, so it will be of some this shape, right? So then that will basically create some non-uniformity in the pressure distribution. So there will be some uh, so so the the lift forces that act on the wing, so those will be non-uniformly distributed, and there will be a net vertical force acting on that. uh, so in this plane, or in this view, it will be like basically the relative motion between the fuselage and engines, or the wing, or basically the wing will deform because of these non-uniform pressure distribution of these lift forces. And so it's like a beam, and then there is another mass attached to it. So the beam will basically deflect, and there will be a relative motion of that. And when if the if there is a change in the pressure distribution with respect to time, then that will cause some oscillations, and that will result in some fluttering of the wing, those kind of phenomena. So you would have also observed, like, how when you see outside the window of when we travel by aeroplanes, like in commercial flights. So then we see that, sometimes we see that the wing is kind of fluttering in some situations. So especially in turbulent weather, it's like very much visible. So the deformation of the wing is substantial in that, in those cases. So let us basically try to model, like basically solve for this. So now here, when we solve for this x1, x2, x3, so here in the figure B, they are actually along the vertical direction. But when we do an abstraction and construct a more simplified model, so then it becomes like a, in the figure C, it is shown is like in some horizontal direction. So that is like just a simplification. So please don't get confused in that. Uh, so it's just a, like a abstraction of that and simplification of that. So it does not mean that we are essentially changing the direction of the motion or anything like that. Okay, so let's get started with the actual solving of the problem. Now, even without solving this problem, can you guess what will be one of the, you know, even without even solving this problem, what do you think is the one mode shape that you would imagine? So recall the one of the examples that we had discussed for 2 degree of freedom systems. So any idea what will be one of the mode of vibration that you can, like, predict without even solving the problem actually? So just recall this example.
1-1, sir. 1-1, sir.
Exactly. So now recall this example where you had two masses and one spring attached, and both the two masses, like, they were not fixed. None of the masses was actually fixed to a wall or rigidly fixed. So then that one of the mode was 1-1, as you said rightly. So which means that the masses simply translate without any stretching of the spring, stretching or compression of the spring. So then that is like one mode shape that you will just get directly, that you, because you can guess it directly here because there is no rigid constraint. So that mode is of no use to us as such, because we already know that the plane can, that translation mode is like just going up and down without any actual flexural, like, deformation of the wing. So here no spring compression or tension means that there is no deformation of the wing. So we know that when the pressure distribution is like very uniform, so then the plane can just move up and down without any deformation of the wing. So that is already, like, it's an obvious thing. But what we are interested is, what will be more interesting to know is when the spring will compress or expand, what will be the mode shapes. So yeah, so let's Now write down the free body, like draw the free body diagram. So for the central mass, now again here we will make this assumption that this x3 minus x2 are and x1 x2 minus x1 are such that the spring remains, let us say, in stretched. So so these will be the free body diagrams for these masses. And then now we can just write down the equations of motion for the system. So it will be basically m x1 double dot is equal to k into x2 minus x1, then m x3 double dot is now we can again similarly rearrange this in a matrix form. So it will be m 0 0 0 5 m 0 0 0 m. So here we get our mass matrix. This is our stiffness matrix. So if we repeat the same steps that we followed to get the natural frequencies, we substituting that x is so we get this the equation of the form. So this is our equation that we get uh, in that form. So we can find out the determinant of this matrix k minus lambda square m to get the natural frequencies. So as we like described earlier. So when we equate this determinant to zero, then we will get the equation in terms of lambda square. So here let us write down that equation directly from the matrices. Now because of the symmetry of the matrix, we can write down some terms directly. Now let us expand this determinant. Now let us here solve this determinant, this expression further. So now let us expand this even further. So we will get k cube minus lambda square m k square minus. So now this term k cube will get cancelled. So we get 5m cube lambda to the power 6. And again this lambda square m k square, this term will also get cancelled. this is the equation that we get. So one of the solutions to this equation will be lambda square is equal to 0. So as we expect that this corresponds to just translation that we had expected. So without any deformation of the spring, and the other two roots we can get by solving this further. So minus 7 k square minus b. Now if we divide by m square, then say k by m is some omega. So we get 5 lambda to the power 4 plus 2 lambda square omega minus 7 omega square is equal to 0. So now what will be the roots of this equation? So it will be minus 2 plus or minus root of 2 square minus 4 into 35 plus 4 into 35 upon 10. So, so it is minus 2 plus 4. So it is 4 plus 4 into 36. Square root of 4 into 36 is 2 into 6, which is 12. So minus 2 plus or minus 2 plus or minus 12 upon 10. So again we get this minus 2 plus 12 upon 10, and so which is 1, and minus 14 by 10. So these are the this this is not a actual feasible route, and lambda square is equal to omega square is one root, so this is feasible. So one of these modes is actually not an actual oscillation, or not an actual natural frequency as such. So whereas lambda square is omega square is, so that is one of the oscillations. So that is basically just symmetrical oscillations of the uh, engine or wings with respect to the fuselage. So that is one of the modes. So that's how we can solve this problem. So I hope that this algebra is not, if it is correct, so then these are the answers. So this, and lambda square is equal to 0 is another this thing which is possible. So that is the translation which we just discussed. So if the algebra is correct, so then these are the I need to check. So you need, so just check again whether if I have like done the intermediate steps correctly or not. Uh, so I am also solving the same problem along with you. So I don't have a ready-made answer with me right now. But basically, conceptually, there should be only, I mean, one mode will be translation and other mode will be actual flexural, like deformation of the spring. Okay, so that's for this problem. So any questions till now?
Sir, can you show the diagram of the problem, sir, which we have shown on the page number 1, where the question has been written, sir?
Okay, this one.
Yes, sir. Sir, actually, I got confused little bit because see, if we take three masses, that's okay. There is a two beams with stiffness K1 and K2. Sir,
Right,
but in the second diagram, we are showing the vibration up and down.
right.
But in the third diagram, we are showing it left to right, sir.
Yeah, exactly.
So,
That's what I told you, right? So don't get confused in that. So because it is just a kind of simplification. See, this is up and down, and see if you consider, like let us look at only this part. So if you draw the, like let us say if M2 was fixed, so then we can write it as a like this, and
yes,
then
like a cantilever beam.
huh?
We can show it like a cantilever.
So it will be like a cantilever beam, and if load is applied like this, so the stiffness of the cantilever beam to a vertically applied load, so it will be this 3 EI by L cube or whatever is shown here. So this stiffness is the basically the resistance to the force acting in this vertical direction. So if we kind of model it like that, this um, so it can be modeled like, so suppose there is a point mass at this tip, so then we can actually model it like this simply. So where K is the stiffness of this cantilever beam, M is the mass at this tip, or mass of whatever the cantilever plus whatever point mass attached at the tip, and K is the stiffness of that spring. So the direction can be like this. or it is also equivalently you can show it like this. So it is the same thing. So x1, x2, x3 directions actually do not mean anything in the figure C. They are basically just the relative motion between the two, between the masses. So it can be either in, physically it can be in the vertical direction, but um, it actually does not mean that the x1, x2, x3 are shown from left to right. So that does not mean that the direction of motion has actually changed. It's just a simplified representation of the same thing. Now instead of uh, assuming a fixed wall, so we have a point mass of 5m here, and similarly the right wing can also be considered like represented in that same spring mass system way, attached to that mass again. So the relative motion between that masses can be represented by these x1, x2, x3. So the direction, for simplicity, it is shown like that. If we had drawn it, if we had drawn the diagram C in a vertical way, it would have been probably less confusing in that sense. But just for simplicity, it is like shown in a horizontal way. But that does not mean that the direction of x1, x2, x3 has changed actually. Do you get that? What I mean to say?
Sir, if we show in a vertical orientation the same problem, sir,
Hmm.
sir, then we will connect 5m in series to m, sir.
Sorry, can you say again?
If we draw the diagram in vertical orientation,
Okay.
so how would we show the mass 5m?
If we
Will
draw
it
it, yeah. So if we draw it vertically, how we will show it is actually the same thing. Only so we will actually see write it in that same way. Like
okay, sir?
it will not change the this thing. Like so, x1, x2, x3 will be like this again. Same. Uh, so same way. Like it's not
Yes, sir. Yes, sir.
changing. So in that sense, like okay. Okay. So two problems we discussed, but like I have like one more problem which we can just quickly discuss. We don't have much time left right now, but uh, so I have this problem here, which was like the car, a model of a car. Now this is like very again similar kind of way, like as I mentioned that we have a actual physical system, and then how do you go from that physical system in reality to a mathematical model? So this is one level of modeling. Let us say if we have like very little information about the car, and like we want to get the idea of what are the different types of motions, like the vibration in terms of vibration analysis. So if we want to kind of study what are the different kinds of motion, uh, so with respect to the relative motion between the front wheels, rear wheels, and the car body. So here this is that kind of model. So the car body is considered here as one lumped mass. Then um, when we want to study the pitching motion of the car body and the relative up and down motions of the wheels, because of the the road, kind of the road gradient, road, like that road surface, variations in the road surface. So the front wheels, let us say, are going over a bump, and then that force, like that bump is being transferred through the suspension to the car body, like car chassis and then body. So then, and by the time the car moves forward, then again the rear wheels will encounter that same bump, and then there will be another type of pitching motion of the car body. So now, in order to study all these things, we need to construct a mathematical model for that. So now, if let us say, um, so what does the mass capital M represent here? It represents basically the car body. So mass of the, so it represents basically the mass of the car body. So along with, let us say, passengers, and so if like driver and passengers, whatever, if it is like relevant, then here the mass m1 represents basically the mass of whatever the whatever is between the the road and suspension. So this damping value C2 K2, so it represents the front suspension. So C2 and K2 represents the suspension of the front wheels. So the left and right wheels are combined together in one single unit. So basically what I mean to say is that C2 and K2, and then so this is one. Now the same damping and the stiffness values are also shown for uh, the rear wheel also. So it can be either front oblique rear wheel suspension. So here, because it is actually shown to be same, so we can say front or rear wheel. So it need not be the same, but here it is taken to be the same. Now this C1 K1, so they represent, what do they represent? Any idea?
Tire, sir.
Yeah, so it represents the stiffness and damping of the tire material. So they represent the tire stiffness and damping, C1 and K1. So they are shown to be the same for the front and rear wheels. So, and masses M1 and M2 represent basically the masses of the wheels, basically front and rear wheels. Now, depending on how much information that we have, we can construct like more and more detailed or simplified models. So here, let us say if you want to also interaction, like understand the interaction between the tires and road, if we have the idea of the tire stiffness and damping characteristics, and also the stiffness and damping characteristics of the suspension. And so then the relative motion between all these elements like the wheels and car body for the front end where, so for a given certain road profile we can analyze or in a simplified way what is the behavior of these different elements by using this kind of a model. Now if we want to analyze in even more detail, then we need to know the masses of each of the four wheels separately and the stiffness and damping characteristics of each of the front and rear wheels and left side and right side wheels suspension characteristics, and also the stiffness and damping characteristics for each of the tire. Then we will know what is the uh, the independently we can analyze the the behavior of each wheel and the relative motion of each with respect to each of them, and then the car body as such. So then we will be able to analyze the pitch and roll motions of the car with respect to that. So then the road profile in the other dimension also can be considered. So here we will be able to, in this with this model which is shown in the figure over here, we will be able to only analyze in that two dimensions. Like in if the road profile is given in that two dimensional way, then this can give us the in more or less in that sense what would be the behavior of that car, the response of that to that kind of a road profile. Now to solve this problem or basically to derive the equations of motion, we need to construct the free body diagrams. So for that we can so here they have already shown this coordinate system over here. So the x3 is taken at the center of mass, and then x1 and x2 are the um motions of basically the displacements of the front and rear wheels respectively in the upward direction, in the vertical direction basically. And then we also need to consider the pitching motion of the car body, so which is shown by theta. So how many degrees of freedom do we have here in with this model?
Four, sir.
Sorry.
Four.
Yeah, so we have 4 degrees of freedom. So because of so we can so we have 4 degrees of freedom, but depending on the coordinate system that we consider, we will get different equations of motion, but they essentially mean the same thing. Then so here with this coordinate system we can derive the equations of motion by applying Newton's second law. So first to draw we have to draw the free body diagram of each component and then write down the equations of motion. So I think we will stop here for today's session since we have already reached the 9 o'clock time. So let us stop here for today, and we will continue discussing this problem in the next session. So if you want, so I will also in the meantime I will also solve this problem for you and then upload its solution. Uh, so so that was all about from my side. So I will also be conducting an extra session on Tuesday, 17th of September in the evening, from 7 to 9 p.m. in this same time slot. So that will be the last session. So this was actually the last session, but I am also taking this extra one on 17th. So that will be the last one from my side. So if you have any questions, comments, etc., so you can get those things in the we can make use of that next session for that. So before we stop, so are there any quick questions that you have?
Sir, some of the question in the assignments being asked, the topic has not been covered in the video lecture, sir. Like question number one of assignment 7 and the question number one of assignment 8, sir. Sir, how to deal with such situation, sir?
Let me just quickly pull up that. Uh, so yeah, so I'll stop sharing the Jamboard. Okay. So just wait for a moment. I am just pulling up the assignment. So your question was with respect to the week 7 assignment. Uh, which week's assignment are you asking about?
Sir, 7 and 8.
7 and 8. Okay.
Yes.
Okay. So let me just open. Yeah. So I've opened the week 7 assignment. So which question are you referring to in this?
Sir, very first question, sir.
Oh, okay. So this question, so if two nodes are observed, okay, okay. So actually this concept is actually I think not covered in your case, so it will not be, it's wrong to expect that one will be able to answer this question because I mean this is like something related to the waves, like wave mechanics, like in terms of the number of nodes, like how the the natural frequency and number of nodes are related. So number of nodes, like, so this 2700 rpm is like, let us say, a higher mode of the fundamental, like the first critical speed is, let us say, corresponding to the fundamental frequency of a wave. So if you understand, like, if there is like just one and then uh, let us say this simply supported beam, so the two ends will have always zero displacement, but let us say in between, um, like consider a sine wave. So if we are so let me just again share back my Jamboard. So I cannot tell you the solution as such, but let me just share with you the concept, because I don't think you should be expected to solve this question as such.
But sir, these type of question may be asked in the examination as well, sir.
Uh, I don't think so, because maybe by mistake it is like, I don't know. I'm not sure whether it is. I don't think it will be asked, because yeah, I understand it is asked in the assignments, but I think in the exam they will not ask this question, because see, so let me just draw this, like, let us say this, there is this sine wave. So these, let us say, are the two ends. So for a shaft, let us say these two ends. So then in the first mode of vibration, so this will be, let us say, the shape, mode shape. And now if you pass two loops, like if the mode shape is like this, then there is this one node in between. And now if you kind of say that if it is like this kind of situation, so then um, so let me just take a different color. So so if it is something like this, so then there are two nodes here in between. So likewise, as you go on increasing the natural frequency, and this mode shape will change, and accordingly, so there will be a relation between the number of like nodes present in that and the natural frequency, and that so all like these waves in terms of, so the wave equation etc. you may have studied in physics, so it has got something related to that. So there will be a relation in terms of the number of nodes that are present, and what is the higher. So you can basically extract the higher natural frequencies uh, by that, like from that. So I don't know. I'm sorry, but I was not able to answer your question fully, but I hope to some extent at least I have answered. What was the other question that you had?
Sir, the similar problem I am facing in the assignment 8 also, sir. But since the due date is still left, so I can not directly ask you the answer, sir.
Exactly. So I cannot really give you the answers, but yeah.
Because, sir, these issues are being raised on the discussion forum also, but actually they are not replying for the last 20 days, sir.
Oh, okay.
Okay, like, sir, in this assignment, the question number 1, sir.
Mm-hmm.
Sir, I am not sure whether I am able to answer this question or not, sir.
Hmm. Okay. Okay. So I
Because
mean, yeah.
because what is meant by the distinct world here, sir? That has been not discussed in the video lecture, sir.
No, distinct means uh, so if
Unique.
the, yeah, unique basically. So let us say if you get a quadratic equation which has equal roots, so then the two roots are like not distinct, right? So they are, so then there is like only one root, so like that. So
Okay, sir.
so in that sense it is like, I mean, I cannot give you the answer directly, but this is like, in that sense you can think of it.
Yes. Thank you, sir.
Yeah. Okay then. So I think then we can stop here for today, and
Yes, sir.
we'll
Thank you.
yeah, thank you. Thanks for attending. So we'll meet in the next session. Okay. Bye. Good night.
Good night, sir.